Welcome everyone. So this is our 90-second live stream geometry. We have 2 people here with us so far, and probably more will join later. And today I'm going to take most of my problems from the Discord server geometry discussions and problems, which I've been doing the past couple sessions. And on that same Discord server, they're hosting a contest that I'd really recommend called the Discord Geometry Olympiad. So there's an individual contest. So they have one for older students and one for younger students. And then they have another team contest. So this is the same Discord server that I take all my problems from this channel on. So in order to support that Discord server, I'd be really happy if as many of you participated as possible. And if you'd like to join our session in the future, feel free to email me at mgreenv801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, and there's one other problem today that I'm going to take from the recent Yasinski Geometry Olympiad. I think it's in Ukraine. I'm not 100% sure, but I will try to get to one of those problems also today. All right, so here is the first problem. So we have a quadrilateral ABCD, and AB intersects CD at S. And then we draw the perpendicular bisectors of AB and CD, and we see where they meet. All right, so I'm going to make these rays. And they intersect at point S. Maybe I'll try to make S a little bit lower. So, but I don't want to make it look like a trapezoid, so maybe something like that. Okay, so this is S. And it looks like Ryan is joining us. Hey, Ryan, thanks for joining. All right. So we just got started with the first problem. AB meets CD at S. We draw the perpendicular bisectors of AB and CD. This almost feels like a generalization of some problem where ABCD is cyclic. Because if ABCD was cyclic, then this would be the circumcenter of it. All right, so these intersect at X. And the line from S perpendicular to SX, we try to see where it intersects those 2 circles. So we kind of have a spiral similarity if we draw the intersection of these circles. That's SBC and SAB. And if we draw the intersection point, a spiral similarity takes EBC to EAB. And let's draw the perpendicular. Actually, let me draw the midpoints of AB and CD.
Yeah, midpoints are really useful since it will make a cyclic quadrilateral. And it will pass through the spiral similarity point.
Oh, are you saying EFXG is cyclic?
Yeah, yeah.
Okay.
With S also.
All right. And
that is because of the spiral similarity, you know, BF over FA is CG over GD.
Okay. Yeah, yeah. So yeah, that is cyclic. And we draw the line from S perpendicular to SX. So it almost looks like X is an altitude, which I don't, yeah, I want to make it look more diagonal. So let me see if I can draw a good figure here. So yeah, if AB is short and CD is longer, I feel like it makes a better picture. So maybe, so it intersects the circles at P and Q. Let's see. So this is P and that's Q. Or maybe the other way. So P, this is Q. And we want to show SP equals SQ. Oops. I feel like this almost feels like a generalization of another problem we did earlier. So is this tangent to the circle? Like, I wonder if this segment's tangent. It is. Okay. So I feel like we did this problem before. I just don't remember exactly. So let's see. Yeah, I want to try to keep X inside the, I think that looks good. It's tangent because SX, yeah, because SX is the diameter. So that's obvious. Okay. All right. So yeah, how did I do this before? So if it were true, we'd have a bunch of congruent triangles. It's the same as saying the power of Q with respect to this circle is the power of P with respect to this circle. I don't know if that helps or not, but. Or it's the same as saying that P and Q have the same power with respect to this circle.
It kind of looks like XBSP is a cyclic. Is that true?
XDSP?
XBSP. It looks like XBP is 90 degrees.
Okay. Let's see if that's true. I don't think that's true in general. In that diagram, it looked like it, but I don't think in general XBP is 90, because then that would mean XCQ would also have to be 90. That's not true. So yeah, I wonder if it's worth drawing the center of this circle. Call it H. I wonder if we can somehow use the power ratio lemma. So the ratio, basically, we want to show the power of Q with respect to this circle.
Oh, I've solved the problem.
Okay.
So we will invert at S. I'm sorry that I interrupted you, but.
Oh, no, it's good.
So I think the main thing about this inversion is to figure out where F and G would go. So you take an arbitrary inversion at S, it doesn't matter the radius.
Mm-hmm.
And this is quite natural to do since we have 3 circles at that point. Okay, so just draw an arbitrary circle and let's see where the points go.
Okay. So you want to see where F and G go?
That would be, I mean, you can draw them, but yeah, okay. And invert the whole picture, so all the points.
Right. So invert X, P and Q.
Yeah, yeah.
I think you can select more than one element at once.
Okay.
Like control or something.
Oh, really? I didn't know that.
Control A, maybe?
Let me try. Yeah, sorry, I'm going to go back. Let me try selecting a whole bunch of ones. So, yeah, I think, yeah, there should be something like for select. Or at least I thought there was. So, well, basically, I think I could just do this, like, whoops. Control. Whoops.
I think select one point and then while holding control, click on another one and it won't.
Oh, okay. Oops, sorry. I'm having a little trouble. Let me try shift. No. Yeah, I know I've seen a way to do it in the past. Move. Let me see. Control shift. Select this point, hold down control. Oh well, I'll just, for the time being, I'll just reflect everything or invert everything. So Q prime, P prime, F prime, G prime, X prime. And those are going to be parallel, and then you want to do E.
Do A, B, C, and D also.
A, B, C, and D. Okay, so draw on some of the lines.
You can scale up the circle to get a better picture.
Yeah, that looks a little bit better. Okay.
Okay, so we just need to figure out what's going on now. We have that C, B prime, and E prime are linear. C prime, B prime, and E prime. That is obvious when circle inverts to a line. Also, you don't need that segment. E prime, A prime, D prime, and E prime, F prime, G prime. Those three are all collinear.
And are these collinear?
Yeah, because Q is the intersection of like this.
They're cyclic, yeah.
Yeah, cyclic, basically, yeah. And now,
E, B, C, Q.
all we need to figure out is what are F prime and G prime, and that we can figure out, but a very, very like neat trick, and that is we can use the fact that inversion preserves a cross ratio.
Okay.
So, for example, C, D, G, and point at infinity, they're harmonic.
C, D, G, and the point at infinity?
Not the inverted ones, the main
original.
Yeah. And C inverts to C prime, G inverts to G prime, D inverts to D prime, and point at infinity inverts to S.
Okay. So those are harmonic. It's S,
yeah.
D prime, G prime, and C prime.
Exactly. And what we need, I mean, we have that PQ is the tangent to this circle that SEFXG. So that line PQ will be just parallel to F prime G prime.
Okay. Sorry, so, PQ is parallel to F prime G prime?
Yeah.
Yeah, okay.
And what we need to show that SP prime is now equal to SQ prime.
Right.
And now you just project the cross ratio D prime, C prime, G prime, S onto PQ, and we're done.
Okay, D prime, C prime, G prime, S, you project it through E prime, right?
Yeah, through E prime onto PQ.
Okay, that's very cool. I like it. I was wondering, so I'm gonna type up that solution. While I'm typing it up, I was wondering, basically by the power ratio lemma, we just want to show the ratio of the powers of Q with respect to these two circles is 2, right? And it would be the same, the ratio of the powers would be the same for any point on this circle. So, I think that makes the solution trivial. Yeah, okay, I found a trivial solution that doesn't use inversion. But
yeah, I see.
yeah, I like the inversion one though, so I'm gonna write it up.
But your solution is shorter.
Yeah, because for point B, it's obvious that the ratio of the powers is 2 to 1. So then it has to be the same for Q. So that solves it. But I like let omega be an arbitrary circle centered at S. And actually, I'll type up both. So this is solution 1. Did we introduce any new points? I guess FG. I'll say let F and G be the midpoints of A, B, and CD. Invert everything about omega. So then we have Q prime, Q, P prime, P, and S are collinear. And then we also have E prime, A prime, B prime, and P are collinear since EADP is cyclic. So EADP is cyclic implies E prime, A prime, B prime, P prime are collinear. I do an extra, oh, there we go. Collinear. So SFXG is cyclic. Cyclic, and that means that S or the point at it, or that means that X, F, and G are collinear, or X prime, F prime, G prime. And so E is also on that. So Yeah, once we know all this, then so CGD and infinity is harmonic. So CD, G, and then CD. That means that C prime, D prime, G prime, S is harmonic. And then projecting through E prime onto P prime Q prime. Goes down to PQ. Then we have Q prime, P prime, infinity, and S. So oops. S is -1, and that means that SP equals SQ. So yeah, I think I just had to add that, you know, these are parallel, which isn't too hard. So why are these parallel? Because this is a right angle. So yeah. So F prime G prime is going to be, but like it's because inversion preserves angles, right? So angle SFX is 90. I'll do it like that. Angle SFX equals 90. That means that angle S prime F prime X prime equals 90. And that means that PQ is parallel to F prime X prime. All right, so that's solution 1. And then solution 2. Solution 2. So we have ESXFG is cyclic. So I'll just use some of the stuff I put above by the power ratio lemma. The power of Q with respect to SFG G over the power of Q with respect to SAD. I think that's what it is. This should be the same as what it is for F. So when I do copy paste, things get messed up. So I'm just going to write this out again. Power of F with respect to SFG over the power of F with respect to SAD. And that's going to be 2 because that's FB times FS. Wait, let me think about this. Oh no, this should be B, sorry, instead of F. B And did I do all my parentheses right? I think I need another one here. And that would be BF times BS over BA times BS. Equal to, that would be a half. And that implies QS times QP over QS squared equals a half. Or I think the other way, right? QS squared over QS times QP equals a half. And that means that SP equals SQ. All right, so I'm going to move on to the next one. That was fun. And let me just tech this up and add a couple parentheses that I missed. So I needed one here and here and make it look better. There we go. All right. So that is the first one. This one's kind of interesting. So we have a triangle with an incircle tangent at point B. All right. Circle ABC, tangent at D, and we have a point E. So E is basically the touch point of the so let me do this. I'm going to cheat. I could just use the compass tool, but this might add some useful structure. So I'll do it this way. So this should be point E right here. Let me call this I. And E. I'll leave that as D prime. All right. T is like any point. Oh, I didn't need to hide that because T is just like any point lying on AE. So we could call this T. And I guess now I'll hide it. Close this. And we draw the tangents from T to the incircle. And we see where they cut BC. And the 2 points that they cut BC at, this is saying that they should be equidistant from D and E. Or not this, well, the distance from 1 to D is the distance from other to E, the other point to E. So I wonder if this almost looks a little bit like Hermophides. So
This is trivial by Desargues involution theorem.
oh, really?
I was just gonna say it looks like DDIT.
Okay, so this problem is too easy then. All right, so let's call this W and this R. Let's see. Just going to draw the other points of tangency. Just okay. All right, so when we apply Desargues involution theorem, so how does that work?
So we apply it to the quadrilateral in quotes A, B, D, C with a conic inscribed being the incircle,
Okay.
and add T. And it tells us that there's an involution on the pencil of lines through T that swaps DT and TA.
Okay.
TB and TC,
Okay.
and the two tangents.
Okay.
And then we project that involution onto a BC.
Okay.
And
So
then
I'm sorry, go ahead.
and then we see that it's that in 4 points, at 4 points it coincides with the one that reflects over the midpoint of BC. So the other two, being W and R, must also be reflections of over the midpoint.
Oh, because reflection is an involution, basically.
Exactly.
Okay, interesting. So Desargues involution theorem just trivialized this, right? Interesting.
Johannes, I have just one question.
Yeah.
How many like lines or points define an involution?
An involution is a projective transformation, so 3 points completely define it.
Oh, okay. Just forgot.
Because it preserves cross ratios. And if you have 3 points, then any fourth one is just defined by their cross ratio.
Yeah, yeah.
With inconic. So you have a conic inscribed in it. By Desargues, so T has to lie on AE in order to, well, I guess you could still apply it even if T didn't lie on AE, but then the rest of the solution wouldn't work, right?
Exactly. Then you can project TA onto BC to get the point E.
Okay. So by Desargues involution theorem, is it the dual of that theorem or it's the normal theorem?
Oh yeah, it's the dual.
Okay. All right. By econ. So we're on our second problem here, and we found that the dual Desargues involution theorem trivialized it. So we're almost on our third problem. So there is an involution swapping B and C, A and B, B and C, and A and B. B and A with D. And it also swaps, I think that's all we need, right?
No, we need that. It also swaps the tangents.
Oh, and it also swaps the tangents. And TF with TG. So does it, do we say like it swaps to lines TB and TC, or do we just say it like swaps B and C?
We say it swaps the lines.
Okay, so and then basically we project this involution onto BC.
Yeah.
Okay. Projecting this involution onto BC, then there is an involution swapping TC, well, TB.
Now we're not. Now we're just considering points on the line instead of lines on the pencil of lines through T. So now we're just swapping points.
Yeah. Okay. Swapping B and C, W and R. and E and D. So it has to be a reflection because since W and R, or since D and E are reflections over M, and B and C are reflections, then W and R also have to be reflections. That's kind of the idea, right?
Yeah.
And so are D and E. Then W and R are reflections over M. Over M, and that means that WD equals ER. Wow, very interesting. Okay, I like it. So that's just the dual Desargues involution theorem. It just says you can take tangents to from whatever this pencil of lines is, like you take the tangents from that point T to the conic. Like that's what this theorem lets you do.
Yeah, in general, we can also apply it onto a non-degenerate quadrilateral, and then it's in some cases more interesting. Then we get already without considering the inconic, we get 3 pairs. So the theorem actually gives us four pairs in that involution.
Okay.
But in the degenerate case, 2 of these just are the same thing. So that's not.
Well, so in the more general case, are there like 4 tangents from this point to the conic? Is that kind of what you're saying?
No, in the more general case, we have some quadrilateral, or some quadrilateral, and that has 6 points, and they come in pairs, and the involution swaps any 2 of these.
Okay.
And then it also swaps the tangents.
Okay, all the tangents from this point to the whatever the inconic is.
Yeah.
Interesting. Very cool. I got to get better at using this because I know people use it quite a bit. And I think I3435 used it to like trivialize another problem on my channel. All right.
There's a really great script by Mark BCC 168 or something.
He has like a paper on it, right?
Yeah.
I'll have to read it a little more. All right. So so this problem, so I'll continue on to this one. So this is from a competition actually. I chose this problem because someone on my channel posted that they created this problem and they wanted me to try to solve it. So I will see what I can do. So K is the center of arc BAC and KW is the diameter. So this is K. AC is supposed to be less than AB. So we could kind of move point A here. And this should be W. Let me draw the midpoint right here. And then we draw the circle touching BC, AB, and AC. So let me think how I want to do that.
That is just the mixed linear circle.
Yeah, it's the mixed linear circle. Usually I like doing it like this. So what I'll do is I'll draw the angle bisector here. And then I'll draw the incircle. And then I will draw this circle. It's kind of how I cheat. So E doesn't necessarily lie on KW. We then have this point. And I think it's like the circle. Basically, yeah, we got to drop perpendiculars. Is it just, sorry. So is this the center? Actually, let me think about this. Why did I draw this? I forgot how to draw mixed linear. Let's see.
No, I think what you're doing is correct. That G is just the incenter.
Okay.
Because the circle you drew is the circle with diameter BI.
Okay.
And then now you need the perpendicular through I to BI.
Okay. So this, right?
Yeah.
Okay. And oh, I'm sorry. The circle I meant to draw, I didn't mean to draw this circle. I actually meant to draw this circle. That's right. That's where I got confused. So this is the center of that circle. And that's the mixed linear. All right. Okay.
Can you rename the incenter into to I? Like it's more familiar.
Yeah, I is better. I agree. So we'll call this I. Let's call this N. And it says that it turns out that, so this is that circle gamma, and it touches KW at point F. Okay, so we want to draw the diagram so that that mixed linear end circle is like tangent at a point, and they're calling it F. So I'm just going to like try to guess it in my drawing. Whoa, was that? Oh, I think if you try to move it exactly, it'll make it so that it's actually tangent. Let's see. Let's call this something else. P. Okay. Okay, so this is tangent at point F to the diameter. So let I, oh yeah, I is the incenter, M is the midpoint of arc 8K. Okay, so I'll draw the perpendicular bisector of 8K. And that is M. And then we want to draw the intersection of MI with the big circle. And so that would be T. We want to show that FI, TW, and BC are concurrent. It's kind of random. Okay, let's see if I could make this look a little better so that MT is a little more slanted. Of course, we still want this circle to be tangent, but maybe I could change. I kind of like that. So we could call this point F. Let's see. Oh, it's thinking F is like an intersection, not really a tangent. Okay, so yeah, we'll just pretend that that's tangent. Well, if it's tangent, then JF should be like perpendicular. Yeah, it's not gonna be perfect, but so yeah, you could just pretend that this is like a rectangle, JF dn. Yeah, pretend that JF is parallel to dn, even though it doesn't look like it. Okay. All right. I'll draw the center of the circle. Call it O.
F should be the in-center of KBC.
ABC.
KBC.
Okay. How did you figure that out?
That is like the Desargues theorem.
Okay. Yeah, because basically you're looking at like triangle KBC, and that's like so like JF, this other circle, and the in-center would all be collinear. So yeah, by symmetry, F is the in-center of KBC by Theorem's theorem. Interesting. All right. Oh yeah, my diagram is that bad.
You should construct a good diagram.
Yeah, so
wait, can you explain why K is the in-center again? I don't see how T-ball theorem apply here.
Mixed linear circle of ABC is the curvilinear in circle of KBC with Chevian KD.
Okay.
And then line FN passes through the in-center, but F lies on the angle bisector.
Okay. Yeah, that's true.
Yeah. Okay.
So I thought, what's the theorem like? So the way I was thinking about it is, if we drew the other curvilinear in circle on this side, so this is the curvilinear in circle for KBC. If we did it for KDB, it would be like the reflection of that circle over KW, right? And Theobald's theorem says that the centers of those three circles are collinear, right? So like that's kind of what I was thinking you were saying. So if I took this circle and reflected over KW, then that should be like the curvilinear circle on this side. And Theobald's theorem says that, or at least what I thought it says, is that like the centers of these three circles have to be collinear. So G, F, and J would have to be collinear. So then F would have to be the in-center of KBC. Is that argument correct? Like I didn't use anything with angle bisectors. I thought it was just that these three centers have to be collinear.
Yeah, I think that is true too. You can explain it either way, Stefan or yours.
Okay. All right. Okay.
Also, I'm quite sure that you should draw a perfect diagram.
A perfect diagram?
Yeah.
Okay.
By starting with KBC and then drawing the curvilinear circle and then drawing the tangent.
Okay. All right.
From what
So
I've seen in a perfect diagram, I see that Km and Di are parallel, and also that Kd and Mi are parallel. In fact, I mean F, not D. KM IF is a parallelogram.
okay. All right. Let me draw a perfect diagram. So
That is equivalent to solving the problem.
Oh,
Yeah. If you can prove that Km and Fi are parallel, then yeah, I think it's done.
all right. So let me redraw point. Let's see. Km. Okay. So I'm just thinking about the best way to do this. Okay, let me just redraw everything from scratch. So first I'm going to draw KBC. So this will be K, B, C. And then I'll draw the center of that. And I'll reflect K over it. So we call O the center, maybe make it a little bigger. All right. Now this will be point W. Okay. And oh, actually, so that really should be, okay, then I'll draw the end circle KBC. And the end center will be F. I probably should have said F. So F is the center of that circle, which I think is E. There we go. And now let's see, how do I draw A? So I think what I could do, that shouldn't be A. B, like I had a rectangle here, right? So it's kind of like I draw the point that makes this a square. And I think that would be the center of that other circle. So let me do that. Whoops, I want to draw this and then this. Oh, wait a sec. So is this actually the center? Let me try something. Yeah, this is actually tangent. So this intersection point right here is basically the center of this curve, this curvilinear. Okay, so let's call this like X. And it's gonna it's driving me crazy. This is always A. Okay. So then we want to draw I. So yeah, how do we draw A? Just do we draw the tangent from? I'm trying to think how we do this.
just draw the tangent to the mixed linear. From B.
From B. Oh, you're right. Yeah, it's that easy. All right. So this is A. And then we draw the end circle of ABC. All right. And then we need to draw M. This is M. T is the intersection of MI with omega. So did you say that, well, what did you think was a parallelogram? Let's see. So you have Fi, TW, BC. Okay. So did we think earlier that KMIF was a parallelogram, or just that KM is parallel to IF?
KM must be parallel to IF if the problem is true.
Okay.
Oh yeah, I see now it isn't a parallelogram, but Km parallel to IF is true, and it is equivalent to the problem.
Okay.
Why is it equivalent to the problem?
Yeah, it is. Can you extend WT to meet IF at a point?
Okay.
By an angle chase, we can prove that BFIC is cyclic.
B. Did you say B, I, and C are on that?
BFIC.
Oh, BFIC. All right.
Because angle BFC and BIC, they are both equal to 19 degrees plus BKC. BKC over 2.
So E has the same power with respect to this circle and the big circle.
Yeah, so that little quadrilateral must be cyclic, FITW.
Yes.
And that thing is cyclic is equivalent to saying that IF is parallel to KM.
Okay.
Yeah, and I think that the problem is just an angle chase.
Showing that those are parallel.
So is that true in general that I lies on the circle around W? Like any mixed linear in circle?
Sorry, but which circle? Oh yeah,
BFC.
it must lies on.
Okay, that's cool.
That is the in-center extender lemma.
Oh no, wait. Oh, I is the. Oh, I thought I was the center of the mixed linear in circle. My bad.
So BIC is 90 plus A over 2. Is that right? I'm just trying to do the math in my head.
Sorry, which angle? Which one?
Oh yeah, it is. Yeah, angle BIC and BFC, they're 90 plus A over 2. Yeah.
Yeah, that is true.
Okay. So did you say you think it's just an angle chase that KM and FI are parallel?
I'm just predicting because those points are not really hard to,
Okay.
do some calculation.
Yeah, angle MKF, that's not too hard to calculate because M is the midpoint of AK. And then this angle, IFK, let's see, sorry. Okay, so yeah, how do we find angle IFW? Yeah, so we don't know this is cyclic, but if we show they're parallel, then that proves it. But yeah, the line IF seems a little tricky to me. So that's connecting the centers of these two. So IF is like, so basically if we draw the common tangents of those circles, it should also pass through E if the problem is true. Maybe we could use Monge's theorem somehow. Although that might be making it harder than it needs to be.
Add in the tangent of mixed linear circle to AB.
Okay.
To AB, line AB.
All right.
And we can use then that the GJ passes through I.
Oh, I think that's like Sawayama's lemma, right?
That is just a standard theorem.
Oh, no, you're right. Yeah, that's just the standard that I is the midpoint of JG. Yeah.
And also BX passes through I, and this looks like useful. Also, we can use the fact that we have a power of a point, so XF squared is XI times XB.
Okay.
Maybe to get some angles.
All right. So XF squared is XI times XB. So from there we have like angle XFI is angle FBX. And that looks like it might, because XFA is 90. So basically we want to show, yeah, I think an angle chase, like once we know that, I think an angle chase would solve it. Because then that would change it to like angle FBI. FBI let's see, FBI is like F. It's half of FWI. And we just want to show that half of FWI is, well, we want to show AI and W are collinear. Yeah, okay, so I solved it. Yeah. But yeah, no, that's a good observation. That's similar. Yeah. Okay, so from here, it's all just an angle chase. This is fun. All right, so a lot of interesting stuff going on in this diagram. Gonna move this as far as I can just to make room. Okay, so I'll say let X be the center of gamma. Okay, so let G and J be the touch points with B, C, and BA. We got a dollar sign. So I is the midpoint of GJ, that's well known. So, and then so K, so I'll say let alpha be the reflection of gamma over KW. Here's where I'm going to use Theobald's theorem, be the reflection of gamma over KW with center Y, let's say, not shown. So by Theobald's theorem, X, Y, and F are collinear. Well, first we want to show F is the, well, this is the proof of that. So yeah. So X, Y, and the in-center of ABC are collinear. And that means that F is the in-center ABC. See how this looks. Okay, and then once we know that, now we want to, first we want to show Km is parallel to IF so that we can show that that's cyclic. Actually, and we have that xi times xb is xf squared. Okay, and we're using that. So xi times xb is xg squared, which is xf squared. Squared, and that means that angle xfi is equal to angle fbx. FBX. And then once we know that, I wonder if we, without even showing their parallel, if we could just, well, we defined M this way. So yeah, we have to use, we want to show that angle. Let's see. So angle IFW, it's 90 minus XFI, which is 90 minus FBX. Which is 90 minus half of FWI. Okay, so we have angle angle IFW is 90 minus angle XFI. 90 minus angle FBI. I'll say FBI here, just to make it clear. So I'm using the in-center x-center lemma here too, which is 90 minus angle FWI over 2. I kind of said it was obvious that this is cyclic, so I should write that out. Angle BFC is BIC. (90) plus angle A over 2. And that means that BFIC is cyclic with center W. That's by the in-center x-center lemma. I don't know if there's an easier way to think about it. By the in-center. Then we have this angle chase. And this is 90 minus KWA over 2. And that's 90 minus oh wait, FBI is half of KWI, which is half of KWA. So that would be like K, which is KOM. So KWA is the same as KOM. So this is 90 minus KOM over 2. Oh yeah. And then, and that is angle OKM. And that means that KM is parallel to IF. And once we know that, so by Rimes' theorem, so I mean, yeah, really it's just an angle chase, but angle IFW is angle, I'll just write it out. Angle IFW is angle MKW is 180 minus angle WTI, so FITW is cyclic. And then we just apply the radical axis theorem. So I'll just state what those circles are, although it's pretty apparent from the picture. By the radical axis theorem on ABC, FITW, and what's the other one? BITC. FI, TW, and BC concur. All right. So I've written it all out. This is a good one. All right, and I will move on to the next one. Sometimes it's hard to see stuff at the very bottom on the channel, so we'll just move it up a tiny bit. All right. So we use Theobald's theorem, we use the n-center x-center lemma, and I think it's time for a riddle. All right, so this